Okay, good day everyone. So, in continuation of our topic last time, that light wave, we'll be looking at the number of images formed by two mirrors. To see this diagram here, this is an object, a candle object. Now, you could see that we have three images of that object formed in the mirrors. Now, these are two mirrors that are inclined at angle 90. This part here is the angle 90 where they are inclined. Now, because they are inclined at angle 90 degrees, we could see three images of the candlelight being formed. Like to tell us that the number of images formed by inclined mirrors, when we talk about inclined mirrors, mirrors that are at an angle to each other, is dependent on the angle at which they are formed. And this is the formula for it. This formula is to help us determine the number of images formed by two mirrors at an angle theta. Now in this case, because they are at angle 90 degree, this theta here represents the angle. Replacing this theta with angle 90 degree here, we have 360 over 90 minus 1. And when you divide 360 by 90, you have 4. So 4 minus 1, that's 3. And that gives us exactly 3 images that were formed. This is the first one, the second image is formed, and this is the third image. This is the third image formed rather. Okay? So we have 3 images formed, because the angle between the two mirrors is 90 degrees. So with this formula here, you can determine the number of images that will be formed when two mirrors are inclined at each other. Okay, so that formula is very key for us in determining the number of images formed. Alright, so moving on to the next one. So we also have the effect of mirror rotation. You know, as you have a mirror, if you rotate a mirror at a particular angle, it has an effect on the reflected ray from that mirror. In this diagram now, we have a mirror. This mirror is on horizontal direction here like this. Okay, and now when you rotate it at an angle theta here, then the reflected ray, which is R1, we turn at 2 times the angle at which the mirror rotates. In other words, if the mirror rotates at angle 10 degree, then the rotation of the reflected ray will be at angle 10 times 2, which is 20. So what we are saying in essence is, when the mirror rotates, the reflected ray also rotates, but by twice the angle of the mirror rotation. This formula is very key in calculation questions and physics. So please, let's take note of that. Okay. Now we go on to the uses of mirror. Plane mirror. Now we're talking about plane mirror. Now one of the uses of plane mirror is that it is used in periscope. This is the diagram of periscope. A periscope is just an instrument used for observing over, around, or through an obstacle. So when you cannot see an obstacle, or you are prevented from seeing an obstacle, maybe because of security purpose, then a periscope can be used. You could see this flower here. The flower, is out of sight from the viewer. But look at the viewer here. This is the viewer intending to see this flower here. But probably because of security purpose, he cannot go on to see. All you need to do is to pick up a periscope, take it up. Now, the ray of light coming from the flower is the mirror. You see the first mirror here. And the first mirror reflects it down to the second mirror, and the flower image is seen by the object here. That's exactly how periscope works, and it's because you have two mirrors embedded in it. That's one of the applications of plane mirror in terms of reflection. Okay, so it allows us to see objects that are above us or around us. All right, now the next use, of a plane mirror is that it is used in kaleidoscope. Okay, this is a typical diagram of a kaleidoscope. It's an optical instrument that consists of two or more reflecting surfaces. This is the kaleidoscope here. To see this kaleidoscope, we have three striped mirrors that are brought together to form this shape here. You see a triangular shape. So there are three mirrors that are brought together. Now, at the end of the construction, the essence of this is for you to be able to see reflections of colors. Now, these are the different colors that have been brought beneath the kaleidoscope. Now, this is where you can view the colored object. By the time you look through via the kaleidoscope, this colored object here, you'll be seeing different colors interfering one another, and it gives a very beautiful look because of the reflection of the mirror in the kaleidoscope. That is another area of application or use of the mirror. Okay. Now the last one is also used. A plane mirror is also used in sextant. A sextant is an instrument that you use to determine the angle between the horizon and the celestial body. Okay, this is the horizon. Okay, and then this is one of the celestial body, the sun. Now you want to determine the angle between the sun and the horizon. Okay, the horizon is just the surface of the earth where it's assumed that the celestial body form an angle. Now, for you to determine the angle between the horizon and the sun, in this case, you'll pick up a sextant, lift it up a little, and once the light ray from the sun falls on the mirror, you see the first mirror now reflect that ray to the second mirror here, which now help in determining the angle. There's the scale here. This scale now gives all the angle that is being measured. So that's how the mirror is being used in inventing the sextant. Okay. Now let's talk about another type of mirror. We're just done with plane mirror now. The other type of mirror that we also have is known as the spherical mirrors. The spherical mirror is just the opposite of plane mirror. In its own case, it's spherical in shape. You see one here. They are just of two types. You have the concave one and you have the convex one. Every mirror has a reflecting part and a non-reflecting part. So we are interested in the reflecting part because that's where we get reflections. Now, for spherical mirrors, like I said, it has two types: concave mirror and convex mirror. Now, the concave mirror has the inside, okay, you see the inside of it to be the reflecting part, while the convex mirror has the outside of it, the bulging part, to be the reflecting side. Okay, so that's just it for the two types of mirror, spherical mirror that we have. Okay, so now how does the spherical mirror help in reflection? Now let's go on to talk about a particular term that we use in spherical mirror, and that's called the spherical aberration. It's just a phenomenon where a spherical mirror of wide aperture or opening, and that word for aperture is opening, cannot bring all parallel rays to the same focus. Let's see an example here. Look at this. Look at this concave mirror, a type of spherical mirror. Now, when the light ray from the star strike the reflecting surface, the reflected rays, you could see they are not meeting at a point. Some met at this point here, okay, this point, while some other reflected ray met at this point. So this is what we call the spherical aberration, a phenomenon where a spherical mirror of wide aperture cannot bring up parallel ray to the same focus. So some brought it at this focus, while some other reflected ray brought their reflection at this focus. So this is a typical example of a spherical aberration. But on the other hand, when there is no spherical aberration, all the reflected rays all meet at a point. You can see all of these reflected rays meet at a point here. So this is what makes this mirror a non-aberration mirror. Okay, so that's it. That's it about spherical aberration. So we need to know these terms because sometimes we might be using them subsequently in our other classes, so we need to know them. All right, so going forward, we also have some characteristics of image formed by either concave or convex mirror. So here we are going to see the properties of images formed. So going forward now look, this experiment is just to determine the characteristics of image form, firstly by a concave mirror. Here we have a concave mirror. This is a concave mirror because the inner part is the reflecting surface. Okay, now this spot here is called the focal point. Here is a focal point. Now the focal point is just the point where the reflected ray passes through when the incident ray strikes the mirror. Okay, let's see what we are talking about. Let's see what we are talking about here. Okay, but before then, let me mention that this is the object. Okay, it's representing the object that the mirror will capture its image. All right, now between the focal point and the mirror, the length between them is known as the focal length. Okay, now where the mirror is located is called the pole. Okay, it's called the pole. Here is the pole of the mirror. The pole of the mirror. Okay, let me label it P. Now the distance between the focal point and the pole here is called the focal length of the mirror. So this distance from here to here is focal length of the mirror. Okay, and now if you observe very well, you find out that between this spot and this spot is equal length with from this spot to where this object is. Now if you add up the two from the pole down to where the object is called the radius of curvature. Okay, the radius of curvature. The radius of curvature is just r, represented with r, equals 2f. 2f, where the f represents the focal length. Remember, I said between f and p is called the focal length with small letter f. Okay, now if we have here from here to here 2 as f being equal length, okay, and we say from here, from where the object is down to where the mirror is our r, we can then say, so that means if we call this place our r, we can then say that our r is equal to 2f, 2 focal length, and this 2f is synonymous to radius of curvature. Okay, now the point where the object is that exact point where the object is, that form the distance between the object and the pole, that particular spot is called the center of curvature. The center of curvature. So between center of curvature and P, we have radius of curvature. Between focal point and pole, we have focal length. So please, let's take note of these terminologies. Between center of curvature and the pole is called the radius of curvature, which is the same thing as 2f. Now between the focal point and the pole is called the focal length. All right. So this information is very important that we do not forget that. Okay, I've only established that now. Now we are going to bring in our ray of light. Remember what we call it? What we call a ray. A ray is the path through which the light source follow. Okay. Now let me put in the ray now. Putting in the ray, we have something like this. You see now. Now you can see. Now this ray here. The ray that is coming from this object, we usually represent it with an arrow, showing that the ray is coming from the object and then it's striking the mirror. Now at the point of striking the mirror, it got reflected. You could see. So this one that strikes the mirror is known as the incident ray, while the one that is being reflected is called the reflected ray. Now I said something about the focal point. Any ray of light that strikes the mirror, the reflected ray must go to the focal point. That's it here. So this particular spot is the focal point. Okay. So then another thing again is any light that passes to the focal point, you can see this one coming from the ray and it passes to the focal point. Okay. By the time it reflects through the same focal point. Okay? When it passes to the focal point, it reflects through the same focal point. So let's take note of that too, because it's the rule of ray diagram. Alright? Now when the light passes through the focal point, it reflects through it. Okay? That's it. That's the reflected ray now. Now when it goes through like this, it goes through the object, it go and hit the mirror, it passes through the focal point. All right, and the next one is when the light ray coming from the object strike the pole, this pole here. Okay, it just reflects without passing through the focal point. All right, so it's very, very key that we know this. And at the end, we find out that all the reflected ray all meet at this point here. This first reflected ray with this second one and the third one all meet, and this particular one too. Okay, all meet at a particular spot here. This is where the image is formed. You can see that the image form is inverted. The image form is inverted. You can see upside down. That is the image form. It's upside down. It's not just upside down. It's also the same size with the object. Remember, I said this point where the object is standing is called the center of curvature. Now, when an object is on the center of curvature, one of the characteristics of the image form is that it is inverted. That's if you could see it here. And also it's the same size with the object. And thirdly, the image is real. When an image is real, that means it's not behind the mirror, it's in front of the mirror. So the image form is real. So three properties or three characteristics of the image form when the object is on center of curvature is: one, the image is inverted, the image is the same size, and the image is real image. Okay, so that being said, let's now experiment again. What if we move our object away from from the center of curvature. Let's see what happened to the image. Look at me now. I'm going to move the object away from it. I've moved it away from the center of curvature. What did you notice? You could see that the image being formed is now magnified. It's bigger than the object. Okay. Now what we can say here is that when the object is between the center of curvature and the focal point, then the characteristic of the image form is that it is magnified, that means bigger than the object, is still inverted upside down, and it is formed behind the center of curvature. You can see it's formed behind it, and it's also real because it's not formed at the back of the mirror. That's it. Okay, so let's move on. Now the ray diagram is now showing this information. Now we see this now, that the incident ray coming from the object strike the mirror, and then the reflected ray must go through the focal point. The rule must be obeyed. Okay, so the focal point is there. Do not mind the diagram, but the reflected ray must go through the focal point. Now when the image is formed, we have mentioned the characteristics of the image. Again, let's experiment again. If we take away this object from between center of curvature and focal point, let's take it a little bit closer to where the focal point itself is. When the object is on the focal point, you could see that the image cannot be found anymore. We can now see that the image form is at infinity. That means we can't see it. When the object is on the focal point, the image cannot be seen. It's at infinity. It's at infinity. But now let's take it a little away from the focal point. When you take it away from the focal point, and you see the image now, the image form is now behind the mirror, meaning that it is virtual image, it's not real. Whenever the image is behind the mirror, it's virtual, it's not real. Okay, it's not real. Now aside that, it's also magnified, it's bigger than the object. It's not real, it's bigger than the object, and it is erect. It's not inverted, it's not upside down. The image form is erect. So three things now about the characteristics of the image when the object is between the focal point and the pole. Number one is that the image form is magnified. Number two, the image form is virtual. That means it's behind the mirror. Number three, the image form is erect, meaning that it's not upside down. Okay, so these are the different characteristics of image form in a concave mirror. Don't forget we are talking about a concave mirror. A concave mirror. All right. Now, when we now consider the same experiment for a convex mirror, let's see what happens. Okay. Now, this is a convex mirror. Now, for a convex mirror is very simple. The image from the convex mirror is always virtual. Now, this is the object now. Anywhere you place the object, the image form is always virtual, meaning that it's always behind the mirror. Okay, the image form is always virtual. That's one, and it's always smaller than the object. It's diminished. That's what you mean by smaller. So the image is smaller or is diminished. It's behind the object, meaning that it's virtual, and it's erect, meaning that it's not inverted. The image form is erect. So no matter the position of this, let's try experimenting it. If you take it behind the center of curvature, it's still diminished, virtual, and erect. If you move it closer, beyond, if you move it before the center of curvature, you see the same thing happens. So these are the characteristics of image form, either in a concave mirror or in a convex mirror. So that's it. It's very important that we have this understanding of this concept. So moving forward, so now we'll be looking at linear magnification of image. Having known that images have different characteristics, there is need for us to also know how to determine the character of this image, especially whether it is magnified or it is diminished. So here is the formula for determining this. Linear magnification equals image height over object height, which is the same thing as image distance over object distance, and then where the linear magnification is represented with the letter M, which is equals to image height, which is hi over h naught, which is object height. That is equal to image distance with v over object distance, which is u. So now we are going to do a little calculation now in our next slide. Mirror formula. The formula for determining image distance, object distance, okay, or even the magnification of the image is this: 1 over u plus 1 over v equals 1 over f, where u there is the object distance, v is the image distance, and f is the focal length. Now let it be known to us that when it comes to convex length, the focal length of the convex length is always a negative number. So we should know that. Now let's consider a question here. It says an object which is 5.0 centimeter high. That means that the height of the object is 5. Okay. Now let's note that from the statement we could say that h naught, which is the height of the object, is 5.0 centimeters. And we are told an object which is 5.0 centimeter high is placed 10.0 centimeters in front of a convex mirror, meaning that u is 10.0 centimeter because u represents the distance of the object from the mirror. Alright? And again, we are told that the focal length of that mirror is 15.0. But take note that the mirror is convex mirror. Whenever the mirror is convex mirror, the focal length is taken to be a negative value, minus 15.0. Even though it's not written in the question, we are expected to know that. Okay. Now find the position, size, and nature of the image produced. Of course, we know from our last slide that in a convex mirror, the image produced is always virtual. So we are expecting to see a virtual image, and also diminished. So we are expecting to see an image that is smaller than the object. So right now we want to determine 3 things. We want to determine the position, the size, and the nature. Now how do we do this? Very simple. Going back to our mirror formula here, we can do this. Okay. So here we have our u in the question already. It's given to be 10. Our v is the distance of the image, and that's what we talk about, the position of the image. So we are looking for that, and our f is given to be 15.0. So applying this formula here, we can say that 1 over our u is 10 over 10 plus 1 over our v is not known, that's what we are looking for, equals to 1 over f, and our f is minus 15. Okay. Now if we make our v 1 over v subject on the formula there, 1 over v equals minus 1 over 15 minus 1 over 10. Alright, and then let me share the screen into 2 parts, and then going forward, now the LCM of 15 and 10 is 30. Now 15 is 30 is 2, 2 times minus 1 is minus 2, and minus 10 and 30 is 3. 3 times 1 is 3. So now minus 2 minus 3 is minus 5 over 30. And then here we have 1 over v. Now if you make v subject there, v there, we'll be giving us, we'll be having 30 over minus 5. That will give us minus 6 centimeters. So it then tells us that the image distance from the mirror is virtual and is 6 centimeters away from the mirror. So we have determined the position of the image now. Know that it's virtual, 6 centimeters away from the image. Now, how about determining the size of the image? Is it big or small? We know that the object is 5. Now, definitely, because we are dealing with convex mirror, let's find out whether truly the image will be bigger or smaller than the object. Now, going by our mirror formula again, we remember that V over U equals HI over H naught, where the HI is the image height, like what we are looking for. H naught is the object height, which have been given as 5.0. V have been determined to be 6, and U have been given in the question. So we say now that 6, replacing V with the value 6 over, and then U with the value which is 10 equals, then HI, that's what we are looking for, over H naught is 5. Now if you make your H high the image height, your subject the formula there, you'll be having 6 times 5 over 10. And that will be giving us 30 over 10. That will give us 3 centimeters. Wow. So this has confirmed that the image form is indeed smaller than the object, because the image here is 3 centimeters by height, while the object is 5 centimeters. Okay, so these are the characteristics of the image form in a convex mirror. It's always smaller than the object, which is called diminished. It's virtual, that's why we have minus 6 here, and also it is erect. It is erect. All right, so that was it about just a little calculation in calculation using the mirror formula. Okay, so we are going to be drawing the curtain here, and then in our next class we'll consider more in a light way. So for now, I would like to draw the curtain here. Thank you for listening. Bye.